Welcome to section 5.6, talking about rank and nullity for a matrix. So our objectives for this section are to know the meaning of and be able to compute the rank and nullity of a given matrix, be able to determine whether a system has a solution and how that is related to the fundamental spaces, solve overdetermined and underdetermined systems, and know some statements, equivalent statements on invertibility. Now, last section we learned about row space, column space, and null space of a matrix. Today we're going to take it one step further. Okay, let's go ahead and quickly review what we found last time. So a basis for the row space would be, in this case, the first row vector and the second row vector. Okay, now we also saw that the row operations will not change the row space, so we could have used the the basis for the row space that we got from the RREF version of matrix A, which we remember was 1, 0, negative 1, and 0, 1, 2. So either this, the first two rows, or the RREF version, we look at the rows where the leading ones were. So let me point that out. So if we go back to our problem from last time, if we RREF the matrix, if there's been no row swaps, where the leading ones are will tell us which rows of the original matrix to use, and where the leading ones are will tell us which columns of the original matrix to use. Now, since row operations don't change the row space, if we RREF the matrix, we can just use as a basis for the row space any of the rows with leading ones. So that was our basis for the row space. For the column space, we found out that it was the first two columns. So we could do 1, 0, 2 transpose and 3, 2, 1 transpose. And our null space for this matrix A, maybe I better be careful here. So row space of A, column space, and null space of A. But the null space of A was 1, negative 2, and 1. Now, the rank of a matrix is the dimension of the row space, aka the dimension of the column space. Notice that the number of basis vectors in the row space and the number of basis vectors in the column space are both 2 here. So that would be the dimension of the basis for the row space or column space. And for this particular A matrix, that dimension is 2. Okay. The nullity is the dimension of the number of basis vectors in the null space. So let's write that down. Which in this case would be 1. Now there's a special relationship that exists between the rank and the nullity, something that we've used a lot throughout the semester, you just didn't know it. So matrix A was a 3 by 3 matrix, namely had 3 columns. If I take the rank and I add the nullity, I will get the number of columns in the matrix. So the rank was 2 plus the nullity was 1. It was a one-dimensional subspace of R3. We find out that we get 3, which was the number of columns in the original matrix. And last time we even solved this matrix with a particular set of constants. And if we take a look at the rank of A, rank of matrix A is 2. And when we solve this guy, let's quickly remember what we got from doing that last time. We get 1, 0, negative 1, 1, 0, 1, 2, negative 1, and 0, 0, 0, 0. Okay. If we take a look at this matrix now, the original coefficient matrix, just this guy, has a rank of 2, and the rank of the matrix that is augmented with the constants also has a rank of 2 because we have 2 leading ones. And you'll notice that 2 is equal to 2. So if we have a system and it has a solution, then the rank of that augmented system will be the same as the rank of the original matrix. So if the system has a solution, then the rank of A will equal the rank of A augment the constant matrix. Okay. So now what I want you to do is take a minute and try this one. So notice how we have the same coefficient matrix, but I changed the constant matrix here, and I'll call this a new B guy. So we'll give you a minute to give that one a try. So I'll go ahead and pause while we do that. Okay. So again, our coefficient matrix has a rank of 2. And if I do A augment by this new B column vector, I get this guy, which has a rank of 3. But notice that this is going to be inconsistent. So there's no solution. So the point we're trying to get across here is if, we'll restate it one more time, if the rank of A is equal to the rank of A augment B, then there is a solution. And if not, then if the ranks are not the same, then it will be inconsistent. Okay. All right. Now let's think about this a little bit more. Let's take this C matrix and we'll have you do a little work on him. I want you to find his rank, his nullity, and then let's take and do the transpose of this C matrix, find his rank and his nullity. Again, we'll let you pause on that to give it a try. Okay, let's compare work. So I RREF'd the matrix C, and I find out that I've got 2 leading ones. So a basis for the row space would be 1, 0, negative 3/4, 5/4, 3/4, and 0, 1, 5/4, negative 3/4, 3/4. A basis for the column space would be the first and second columns of the original matrix. And so since each of those bases of row and column spaces have 2 vectors, they will be a rank of 2. And the nullity is the number of columns minus the rank. So 5 minus 2 is 3. If we take C transpose and reduce row echelon form that guy, we get this matrix. And notice that the rank of C transpose is 2, and the nullity of C transpose is 1, because we have 2 non-zero rows here. And so we'll have 2 vectors in our basis. and there was only 3 columns, so 3 minus the rank is going to give us the nullity. We'll pick up there in the next video.